That's perfect. And in the meantime, I will briefly introduce Shubham Tulsiani. So he's a professor of computer science at CMU. He was a research scientist at FAIR in Pittsburgh and obtained his PhD at UC Berkeley. He has a long history of work in 3D reconstruction of images, and recently has worked also in robotics and interaction. He won the Best Paper Award in CVPR 2015, and he's interested in general in building perception systems that can infer the spatial and physical structure of the world they observe. I'm looking forward to his presentation.
Great, yeah, thank you for the introduction and thanks for having me here. So yeah, today I'm going to talk about Sparse-view 3D reconstruction. And I'm really glad Jitendra gave a talk before me on essentially the same problem that allowed me to cut a few intro slides and make the talk a bit more focused on some more results, etc. But really the problem that I want to talk about today is, given a very small number of images of an arbitrary object, such as this fire hydrant or this monitor, we want to get a 3D model out for this. And in particular on this problem, I'm going to talk about one specific work that is based on an upcoming NeurIPS paper of ours titled Neural Reflectance Surfaces for Sparse-view 3D reconstruction. And really sort of Jason and Gensheng did all the hard work. So if you ever run into them in ICCV virtually, just let them know. Actually, I see something in chat. Okay, sorry. So the long-term goal that a lot of us working in 3D vision are really motivated by is this, right? That given just a single image or a very small number of images of a scene, we want to predict a 3D representation of the underlying world. For example, for this living room, we really want to infer all the furniture items, place the sort of cup on the table, and really reconstruct a lot of detail of this particular 3D scene. And while that's a very challenging goal, sort of an intermediate problem that a lot of us have identified as being an important one is, instead of trying to reconstruct sort of entire scenes, first we should at least develop capabilities of being able to reconstruct all the objects in them. So here are just some different objects reconstructed in 3D from some of my recent works. And the hope that we have in the community is really that we'll be able to scale this sort of an approach to really the tens of thousands of object categories in the world. And so with this in mind, that we really want to build approaches that eventually work on these tens of thousands of object categories, I want to very briefly paint the landscape of the 3D reconstruction approaches that we have developed over the decades. And to sort of borrow Jitendra's term of this landscape of approaches that aim to sort of 3D-fy objects from images. And so the axis that I was talking about was this generality, which is, how many categories of these objects can a particular approach reconstruct? So for example, if I were to just go and download the code that the authors have provided, how many among the tens of thousands of object categories, let's say from ImageNet 10K, will I be able to reconstruct? And sort of the other axis, which is kind of complementary to this, which is how much effort do I need to put in to get the 3D model of a new object that I'm interested in? And in this, on one extreme lies a lot of single view 3D reconstruction that we're pursuing. For example, I just want to be able to take one image of an arbitrary object and out should come a 3D model. And sort of on the other extreme is this very dedicated scanning setup. For example, here is a scanning setup that I think Paul Debevec had to get a 3D model of President Obama, which really has many calibrated cameras with very sophisticated lighting to get an accurate 3D model. And so we really ideally want an approach that's somewhere to the top right of this chart. And in fact, the very first computer vision thesis was also tackling this problem of 3D object reconstruction from a single image, and kind of falls in the bottom right corner of this chart, where it could infer 3D from a single image, but was really limited in terms of the class of objects it could handle, just typically limited to these pyramids or cuboids, for example. And over the next decade or so, we improved the generalization by using, let's say, model-based detection systems, which could make it work on a far broader set of categories. And sort of in parallel, in computer vision, there was this amazing stream of work on multi-view stereo and structure from motion-based approaches, which gave a very different perspective to the problem of 3D-fying scenes and objects. And so they tackled a different space of this chart, where they were really general approaches that could, in principle, reconstruct any scene or an object, but required many images and often calibrated cameras to be able to do this sort of an inference. And sort of more recently, with the advent of some learning-based approaches, I think we made a lot of strides on being able to do this in a more general setting. For example, this work from Anju could let us reconstruct meshes of more generic categories from images, again, from, let's say, just a single image. And maybe sort of a very brief self-advertisement of a recent paper that we had in CVR 21, which maybe pushed the number of categories that we could handle from maybe tens of categories to, let's say, 50 or so categories by using some more unsupervised techniques that did not rely on key point annotation. And so, we've been pushing on this towards getting to maybe from 2 categories like faces and cars a few decades back to maybe 50-ish categories at this point, and we can really reconstruct. And sort of the hope is that we'll be able to push this further. But sort of on the other hand, a lot of these nerve-based approaches have improved the quality of what we can reconstruct, and still allow us to reconstruct these very general scenes of arbitrary objects such as this microphone or hot dog, but again require a more painful capturing process where we have maybe 100 or 50 images of a specific scene, with, in this case, very precise cameras as well. And more recently, I think over the last year or so, for example, some approaches have actually looked at relaxing the capture setup. For example, this IDR paper or the BAF paper from Yari Van Lin relaxed the camera assumption from saying, okay, we don't require very precise cameras, but only approximate cameras that, let's say, have Gaussian noise, which we can sort of argue whether it's a realistic assumption or not. But they have allowed us sort of simplified the capture setup a bit to saying, okay, we still need many images, but perhaps the cameras need not be that precise. So still often requiring something like 50 images to be reconstruct a scene, but relaxing the camera assumption. But we still see that there's this wide gap between some approaches on the left, which really work in settings where Colmap can give us rather precise cameras, and some of these single view reconstruction approaches on the right, which don't really require cameras and require just a single image. And I think in the middle is this problem of sort of sparse view reconstruction in the wild, which is what our approach tackles, where we don't really have a lot of images. So something like just 6 to 8 images of an arbitrary object with very coarse and approximate cameras. And so someone can just go around and click some photos of an object they want to sell. And we want to be able to reconstruct objects in this setting. So just to be maybe more concrete, one use case that our approach was really motivated by was this marketplace setting where, let's say, someone who wants to sell their car on eBay can just naturally take, let's say, 8 images of the car that they want to sell. And given this, we want to be able to predict a 3D model out. And just to convince you that this is a really hard setting, here's sort of a typical result of Colmap on some of these marketplace settings. So I think actually this is not a result on this specific sequence. It's a result on a sequence with even more cameras, maybe something like 12. But still a sort of typical sequence. And Colmap, because these are views with very little overlap, doesn't do very well in registering them or getting even a sparse 3D output. And here's actually maybe the best result that the first author Jason got by trying Colmap on maybe 20 or 30 different image sets, where given on average 8 images of different cars, we could register some correspondence and get some plain output, but the car doesn't really look very well. Look very good from the top because a lot of these correspondences are false. So really this setting of sparse view 3D, where there's very little direct overlap, or there's sort of a wide baseline setup across different views, is really challenging for some of these classical settings to come up with very precise cameras. And it is in this setting that we want to be able to reconstruct 3D. And in our work, what we do is, in addition to these images, just use a very coarse initial shape. So in this case, something like a typical sedan-like car, and using initial cameras from learning-based systems that don't give us something like a Gaussian noise, but give us maybe okay cameras for certain views and cameras that could be very off for some other views. So using just 8 or so images and a very coarse template mesh and cameras from off-the-shelf systems, what our work does is tries to get the 3D model of the underlying object while also modeling some view-dependent appearance. So this is really an image that has been taken out in sort of outdoor scenes where there's a lot of lighting, cars or specular surfaces, and we want to be able to model this sort of a view-dependent appearance effect from just these small set of images. And here's maybe just another example with a different object captured in the lab, where again, for this monitor, we just took 8 images, used only a cuboid-like mesh with very coarse initial cameras. And again, we can get a pretty detailed 3D model output using our approach. So before I go into the specific details of our approach, I just want to, oh, sorry, actually, here's just some more results to convince you that this is really something that works across a lot of objects. And again, using the very same initial shape, we're showing reconstructions of about 200 different cars from Craigslist, again, using just about 8 images on average for each of these instances. Yeah, so sort of before going into the details of our approach, of course, this is really inspired by a lot of recent progress in neural rendering work, for example, NERF, which, as I said, lets us very accurately model a very wide class of scenes and sort of get results like these, where we can get accurate 3D reconstructions of very complex shapes with very complex appearance. And so, what is it that makes these neural rendering field approaches work really well? And sort of Anju gave us a very nice review of the math, so I'll probably skip that. But sort of the high level idea is that NERF gives us a very powerful model of geometry and appearance. And in fact, it allows us to model arbitrary geometry and appearance. It is, the per point density model is something that can let us model something like cloud. And the per point radiance field is something that lets us model very different appearances for the same point in different directions. And this really rich and powerful representation of geometry and appearance, given hundreds of images, lets us reconstruct very accurate shapes as well as get very accurate novel view renderings. Now, unfortunately, it is this exact same thing that makes NERF not work very well in sparse-view settings. And so sort of to paraphrase from a famous American movie, if we have a very high representation capacity, then there's a very high risk that we'll overfit and sort of go into some local optima. And just to sort of illustrate the point, this is just vanilla NERF, which we'll actually improve upon as our baselines. But given just 8 images of a generic car with very approximate and not precise cameras, the novel views that just vanilla NERF from off-the-shelf generates are not at all very realistic, because if we look at any of the training views, we actually find that it can reconstruct them rather well. But because the space of solutions is so large, it has really overfitted to the training views and doesn't really generalize to any novel view. And so the novel view renderings with a different elevation and azimuths don't really look realistic at all. And so our solution that really builds on these neural reflectance surfaces actually combines 2 very simple ideas and sort of really combats the arbitrary nature of the geometry and representation that NERF allows. And the 2 ideas are, one, that almost all objects that sort of we are considering have well-defined surfaces. And the second is that the view-dependent appearance, while it's important to model that, for example, specularities in outdoor scenes, this cannot really be arbitrary. We have a lot of well-known view-dependent appearance models in graphics that are far more constrained and represent more closely what happens in the real world. And we should incorporate these kind of knowledges. And it's just really a combination of these very simple and basic ideas that we build upon for our approach that allows us to learn 3D inference from in the sparse-view setting. So just to very quickly go over the shape representation, because I sort of more want to talk on the appearance representation. We model shape as a surface that is sort of diffeomorphic to a sphere. So given any point on the surface of a sphere, we have a neural network that predicts a deformation for it. So given sort of a UV point in the sphere, you map it to a 3D coordinate XYZ. And because you can do this for every point in a sphere, it sort of induces a deformed 3D shape through this neural network. And this gives us some very nice properties that it just guarantees a watertight surface by construction. And sort of similar to what we do in neural radiance fieldworks, using some sort of positional encodings to encode points in a sphere lets us still capture reasonably high frequency shapes, such as the monitor that we saw earlier, which had some of these thin structures. And so the shape representation at a high level is just extremely simple. It's a neural network that maps a point on a sphere to a 3D coordinate and thus induces a deformed mesh. In terms of modeling view-dependent effects, just to maybe give you a bit of a background and notation, what we are really interested in modeling is if we are considering a particular point X and viewing it from a particular point V, how much light will we see emanating from that particular point X? So just to give an illustration, suppose we are rendering this surface and there's this point X that we are viewing from the camera that is in the direction V. how much light will this particular point throw in the direction of the camera. And there's this very old and classical surface rendering equation, which tells us sort of the math behind this. And sort of while this looks slightly scary, it's the equation is just very simple. All it says is that when we are considering the point X, let's consider all incident light directions, omega. And for each of those directions, let's consider how much light is incoming to that point. So that's sort of the last two terms. And what fraction of that light will go back towards the direction V. So essentially, all it's saying is that let's integrate all the light coming into the point X and calculate how much of it will go back towards the direction V. And so this is some very, very classical and well understood thing in computer graphics, which can allow us to model view-dependent effects. And the radiance field solution, or the neural radiance field solution that, let's say, NERF adopts, is to say that, let's just forget about all this. And what we can do is just model this outgoing light from a particular point X in direction V through just a neural network. And we can just learn this neural network. And instead, what we, and sort of just to go back, while this is a very powerful idea, it really fails in the face of limited amount of training data. And so our idea is that we can constrain this particular solution, that we really understand from graphics what are some possible models of VRDF, what are some possible models of incoming light. And so we can constrain both lighting and VRDF models to sort of get solutions that still look realistic and can be trained with little data. And so to be more concrete, what we do is adopt sort of an environment lighting model. So what this says is that the incoming light to a particular point is independent of the particular point and only depends on the environment. So this is something like a car in an outdoor scene, which has no lights nearby, but only sort of the sky that is lighting the particular car. And the second assumption, I'm going to skip some technical details. And the second assumption is that instead of modeling a full BRDF, we can just decompose the view-dependent effect using a Phong reflection model. And this just breaks down the appearance at a particular point into diffuse and specular components. And I think in the interest of going to results, I'll skip a lot of the details. But essentially, we can compute the net incoming light at a particular point and multiply that by the sort of inherent texture at that particular point, which can again be modeled as a neural network, and some specular effects, which model the incoming light and the outgoing direction. And based on some specularity coefficients that we'll also learn, predict how much specular effects we'll see in a particular viewing direction V when we are seeing a particular point X. And maybe just to give you some illustration of what these typical terms look like, if we are trying to render the particular car that we are learning from this reference camera viewpoint that corresponds to this image I, here are the surface normals of the geometry that we can render. Here's maybe just a final texture that is unwrapped that we are learning. And this is kind of an environment map that we typically end up learning, which in this case is saying there's more light coming from the top than from the bottom, let's say. And using these, sort of using the environment map and the surface normals, we can compute the diffuse lighting at any particular point. And that can let us render the view-independent diffuse texture. And using all of the sort of the normals and the environment map and the material properties, we can also compute the specular effects at that particular point. And here's just an illustration of how some of the specular parameters control appearance. But by just a combination of these two, the specular lighting and the diffuse image, we can get this output, which has both view-dependent and view sort of agnostic effects. That can really let us model sort of the shininess on the surface of the car, for example. And so once we have this way of rendering, we can just train our system to match the training images that we have using just simple reconstruction losses. So again, we assume we have at least coarse foreground mask given by mask CNN, and we just say that our renderings should match both the appearance of the pixels as well as the mask when we render this through the rendering model that I just described earlier. And to be more concrete, what we learn are the shape, the per pixel texture, and the environment map lighting. So all of these are neural networks that model the respective properties. And also we optimize the cameras associated with each of these views and alpha and K, which control how much specular the surface will be. And to do this, as I said earlier, we assume some initialization in the form of a very coarse category level template shape. And sort of in this case, we construct a spherical mapping to this so we can initialize a neural network. And we assume very coarse cameras that are given by some off-the-shelf system, in particular this particular system, which takes actually a CAD template and can give us some approximate cameras given an image. But yeah, just sort of given these two and a very small number of input images, we're able to reconstruct these kind of objects given just images from Marketplace. And just to highlight some results, so given these 8 images that we are showing as sort of the nearest neighbor to the current view in the rotating 3D shape, we can get pretty accurate 3D models of the car. And on the right, we are also showing just some visualizations that highlight the view independent and view agnostic rendering effects. And what I kind of want to highlight here is that using just the same initial shape, so just this sedan-like initial shape, we can model all of these 3 cars, which have pretty different geometries from each other. For example, there's a truck at the bottom, or this CRV at the bottom, and the Jeep at the top. And all of these are actually very different from the shape that we initialized with. And again, sort of going back to this image, we are able to reconstruct about 200 different cars using, on average, 8 to 9 images with just off-the-shelf pose estimations and off-the-shelf camera estimations. Sorry, off-the-shelf mask estimations. And so one thing that I do want to very briefly touch upon is how we can evaluate this, because we are really interested in making this work in the wild, where we don't really have ground truth 3D shape for the object that we're interested in. Well, what we can do is hold out certain images and ask whether our learned models can generate those held out novel views. So what this looks like is we have a few input images. So for example, we have 7 input images because we held one out. And given these input images, our approach and any other approach that we consider as a baseline can learn some sort of a 3D representation. And then given a held out target view, we can just query whether this 3D representation can synthesize this particular image or not. And this is the typical way that almost all view synthesis papers, for example, NERF, evaluate how well they're performing. And one thing that sort of is swept under the rug is that the assumption for view synthesis is really that we have ground truth cameras during training and aligned query cameras at testing. So when we say that we want to generate this particular view, we know what precise camera we are talking about. And that, unfortunately, we don't quite have in the real world. Like if I'm taking these 8 images from Craigslist, we don't have precise cameras during training or testing. And so we need to be able to account for this when evaluating the 3D inference that we can make. And so to work around this, in our paper, we actually proposed 2 different evaluation setups. One where sort of the first author, Jason, manually sat and optimized cameras and tuned them so that they're as accurate as possible on a small set of images. So that really represents the classic way of evaluation, except in this case, it's sort of manually defined pseudo ground truth cameras. And second is that we can allow camera optimization during training and evaluation. So when we say that we want to generate this held out image, we should also be able to optimize the camera that we are viewing it from, because the camera that we have from the off-the-shelf system is not always precise. It may be off by 10 or 20 or 30 degrees. So a method should be able to optimize the camera to generate any target view. And I might sort of skip some of the details. And we, again, evaluate this in a data set that is built off of Craigslist, where we chose 20 different image sets, and we compare against NERF and IDR and some other variants as well. And I'll actually just skip to the second kind of an evaluation result, where we do allow fine-tuning the cameras during both training and evaluation. So once you've learned the model, you're allowed to change your camera to best match the target image that you're trying to generate. And we think this is really critical for being able to evaluate by view synthesis in the wild, this ability to optimize cameras during training and evaluation. And sort of in this particular case, our approach is really better than some of the other baselines. And here I'm saying NERF star because we improved NERF a bit by giving it additional foreground mask supervision and sort of regularizing it to only reconstruct within a canonical volume, etc. And all of those tricks made the results sort of comparable. So it's not sort of quite vanilla enough. And here is maybe just some visualization of these different methods of what kind of results you can reconstruct. And you really see that not constraining the appearance model gives very different or sort of jarring view dependent effects, where we see sort of these ghosting artifacts from views that are maybe not seen in training. And so far I'd just been showing results on cars because that was the setting that we were typically evaluating on. But nothing in the approach that I described was really restricted to cars. Really, we can take, because we're in Pittsburgh, take 8 images of the Heinz ketchup bottle, and given just a very coarse cuboidal initial shape, we can learn pretty accurate 3D reconstruction and also model some of the glossy view-dependent effects, and can do this for other shapes such as this PS5 controller, again, starting with just this cuboidal initialization and very coarse camera poses. And yeah, maybe just a few more results on some different scenes, where again, we can capture different kinds of shapes, though we don't model all of the details very well. For example, the milk frother in the espresso machine isn't captured quite well. But in some other cases, such as the fire hydrant or the desktop monitor, we are able to capture a lot of the details. And sort of, I think one interesting ambiguity that comes out is because we are modeling view-dependent effects that sort of are determined by the environment lighting, there is this inherent ambiguity that whether the car is sort of black and there's a lot of environment lighting out there, or whether the car is sort of gray and there is less of environment lighting out there. And so this is something that we really can't resolve in any model, but the output radiance that we get is still plausible. And one other limitation was that we were considering only sort of white environment lighting. And so the model doesn't do very well in the scene at the bottom, where the environment lighting is sort of more yellowish than white in this particular case. And just to very quickly highlight some future directions, I think one constraint of our approach is that it really is restricted to fixed genus surfaces, because we start with a sphere, or we could start with a donut, and we're modeling surfaces that are diffeomorphic to the initial geometry. And it does not, for instance, let us model things that have very thin structures or something like bagels. But for instance, some of the previous talks that we saw could address this, and you could imagine marrying this with the appearance model that we have built in our work. And talking of the appearance model, we were using a very simplistic Phong reflection model. And there are a number of generalizations that one could make to model more complex appearance or geometry. For example, use more powerful appearance models, or allow sort of variation of models or materials across different points on the 3D shape. And this one other limitation, which I think is really, really fundamental, and I don't think as a community we have very good solutions, which is all of these approaches still require at least some coarse camera optimization or coarse camera pose to begin optimization. In our work, we were relying on some off-the-shelf systems, or in some cases with very coarse annotations in 30-degree azimuth increments. But this is something which we don't have very clear ways of overcoming. And if we could, then this would really enable scalability, where we could just download K images of an arbitrary object and be able to run systems such as ours. But yeah, with that, I think I'd like to maybe leave you with this picture, where I really want to highlight that we have done a lot of great work on scaling up single view reconstruction, or getting accurate reconstruction in settings where we have sort of 50-ish images, but being able to do this sort of sparse view reconstruction where we only have maybe 5 to 10 images of a specific object is a very interesting and challenging setup. And I hope we see a lot more work in this. Yeah, with that, thank you. And I'm happy to take questions.
Thanks a lot, Shubham, for the presentation. Very nice results. There is a question from Shangce, which is actually very much the same question I wanted to ask, and I think partially you answered to already. That is, how critical are the initial shapes? Because the impression is that later you show a cuboid, and it doesn't seem to be very important that it is too close, but maybe you can say something more about it. It seems maybe you can start from a sphere, it would still work.
So I think it really is a trade-off between how accurate your cameras can be and how coarse your initial shape can be. So in our case, the cameras were sort of really coarse in the sense they were annotated for some of these objects within just 30, 40-degree azimuth bins. So if you have more precise cameras that you can trust more, then a coarser initial shape is fine, because at initialization, you can refine the shape if you trust your cameras. But if you don't trust your cameras a lot, then, so in our case, we couldn't start with a sphere. We at least needed a cuboid which had the correct orientations, because otherwise at initialization with bad cameras, we would very quickly get stuck in some weird local optimas. So I think the question about how accurate a shape do we want is a great one, but I don't think it's an independent question of how accurate cameras do we have. It's really the combination of the two that we should be thinking about, and together relaxing the accuracy of.
Okay, and I suppose you could also, as Jitendra did, use the call map to get some initial poses, right?
So actually, surprisingly, in our settings, maybe because these are in the wild images with a lot of view dependent effects, we did not, like Colmap did not work at all on any of these sequences. So if you have 8 images of a random car with very shiny and view dependent effects, we did not see Colmap to work. Like we could not get Colmap to work and give us even reasonable initial camera estimates.
Okay. There's another question. Is there any approach which is volume-based, which is a volume-based representation?
Yeah, so I think that's a great point. And I sort of swept some of the comparisons under the rug, but there was this recent work on IDR by Yarev et al., I think last year ICCV, which has this STF representation. So it is sort of volumetric, but it more explicitly imposes a surface-based prior. And that can maybe let us sort of serve as an initialization, except, it all becomes a bit murkier, because if you're trying to optimize these kind of volumetric approaches with very coarse cameras, they do often not tend to converge to a good solution. So I think it's really, if we had good cameras, then I think a volumetric approach would give us a good initialization, because even though it has more flexibility in the regime of good cameras, it will go to a good solution. But I think it's not very reliable if the cameras are far more approximate, as was in our case. And in the paper, which will hopefully be out in archive next week, we do show comparisons to IDR, and you will see that some of the geometry is not as accurate.
Okay. I have also another question, which is, do you need explicit masks in your optimization?
Yeah, sorry. So yeah, that's a good point. And we do have a mask loss. So for all the cars, we use mask RCNN to get sort of some approximate foreground masks, and we do use them in our optimization. And that is, again, sort of critical to making this work.
Okay. And by the way, since you added all these additional, say, generalization in the rendering of the image, did you design your own differentiable renderer to also handle the reflectance and?
So our differentiable renderer can be viewed as two things. One, if we have a pixel, what point on the mesh or the sphere are you rendering? And so that's sort of the rasterization process, and that we used an off-the-shelf rasterizer like PyTorch 3D. Once the rasterization is done, to compute the lighting at a particular pixel, there we sort of wrote our own code, which essentially did Monte Carlo rendering of integrating over all the viewing directions. But I'd like to mention that it's still very, very fast, and actually we could render the whole image almost in real time, and could use things like perceptual losses, which approaches like NERF, for example, cannot, because they're limited to rendering individual pixels.
Okay. And so maybe one last question. So what do you think is the next step in this kind of line of work?
Yeah, so I think I was maybe trying to allude to some of those. I think there are really 3 things. One, we want to we want to allow more generic topologies. Second, we want to capture more complex appearance. So I think both of those we have some handles on how to do. For me, one of the larger open questions is, how do we get these approximate cameras? Like if I give you 4 arbitrary images of a generic object, we can't get cameras using a learning-based system. So just how do we get an approach that can even bootstrap learning? And that to me is sort of something that will really unlock application to a very broad class of things if we can solve that.
Okay. Well, I don't see additional questions. Then thanks a lot, Shubham, for the presentation and for answering all the questions.